second day is always better than the first day. It's a little faster. You can see drastic changes. All right, raise your hand if you got 48 on side A. Okay, we got a few groups that are ready. Good, good, good. Now, the first round on page 501, the instructions say to work in teams of 3. You're only working in teams of 2 or 1. You folded a piece of paper in half and labeled one side A and the other side B. You both placed 48 small blocks on the pile inside A. Now, what we are going to do is we're going to use these blocks as a model of a chemical reaction coming to dynamic equilibrium. What type of equilibrium? Dynamic. Now, when you hear the word dynamic, what do you think of? Dynamite. What else? Somebody said you're really dynamic. Interesting, complex, maybe exciting. Okay? Not dull. Okay? Now, dynamic in chemistry terms or physics terms means to be in motion or to be moving. So usually people that are dynamic get other people to do something, to move. Okay? But that dynamic characteristic is what we're going to look at today. Now, to do this, you're going to move the blocks from pile A to B, from A to B and B to A using certain rules. These rules are called rate constants. This particular reaction has the rate constant of A going to B. You take half the blocks from A and you move them to B per round. The other rule is the rate constant from B to A, as it says on the page, is 1/4 per round. When you move the blocks between piles, you will move them at the same time, which means simultaneously. So, we start out with 48 in A. Does everybody have 48 in A right now? Okay. So, what's half of 48? 24. 24. So, you're going to count out 24 of them. Yes, sir? 501, it's after lesson 3. 501 is right after lesson 3 in the lab manual. This is a really great activity to show dynamic equilibrium. That's why it is a little out of place in terms of the numbering and stuff. Now, what you're going to do, you've got 24 in A that are supposed to go from A to B. But you have to simultaneously, by using your other hand, move blocks from B to A. However, how many blocks are in B right now? No, you haven't moved them yet. How many are in B right now? 0. What's 1/4 of 0? 0. 1/4 of 0 is still 0. So you're going to pretend like you're moving 0 of them. I know it seems kind of ridiculous, but please just do it. So you do it simultaneously. It's a good habit. 24 go from A to B, and 0 go from B to A. Get your hands on them. See if you can hold them all in one hand if you can. Ready? 1, 2, 3. Switch. And drop them. Okay. That was round 1. Now you're in round 2. How many blocks are in A at the beginning?
48.
No. How many blocks are in A right now in round 2? 24. How many are in B right now? 24. What is half of 24? 12. So you're going to take 12 from A and move them to B. But you have to also also do the opposite. In B, you take a quarter of 24. 6. You take 6 from B and 12 from A. You pick them up at the same time and you whoop, switch them. Please move all the blocks you count. Simultaneously. Okay. Now, we are now in round number 3, which is blank on your worksheet. So the first thing you need to do is count how many blocks are in A right now. And write that number down. Then you count how many blocks are in B and you write that down. Now you are going to continue the process of transferring according to the rate laws until you fill up the entire table. So you may continue on with the process, do the same thing you just did in round number 2. Same thing, yep. Yeah, these are the rules here. Here's the rules, and then here's the guidelines. On the instructions, it says if you get like 6.5 or something, you round down. So you can't have half a block. Unfortunately, our models can't split blocks in half. And you're more than welcome to use your calculator. Yeah, round down. It says it in bold on your paper. You round down if you come in contact with a half of a block or something. Or a third of a block. Or ladies and gentlemen, we're going to look at our results from these models, so please return to your seat. All right, I need your attention up here. In this activity, a type of equilibrium eventually is reached. In the first model, okay, how many blocks were going from A to B and B to A during equilibrium? 8 of them. What was not the same at equilibrium? Okay, the piles were not the same. The amount of A and the amount of B were not the same. You had how many in A? 32 in A. Oh, nope, you had 16 in A, sorry. 16 in A and you had 32 in B. Okay, the amount in the piles were not equal, but the amount going back and forth was equal. Okay, this is called equilibrium. What I'm going to ask you to do right now is put all of the Legos away right now and return to your seat, focused and ready to pay attention. If you built anything, you have to disassemble it before you put it away. this will sum up our unit. Today we'll be learning some things about equilibrium. Tomorrow we'll be learning how to control or change those things. The quest fire review. Some people wanted to do that for extra practice. Okay, that's due at 6 p.m. on Thursday. And there is a showtime quest for reviewing for the test on Friday. The showtime quest is only 20 questions, and it is out of 50% instead of 100%. So if you get 100% on it, you get 50% extra credit on it. If you don't do it at all, you could lose 50% obviously. But if you get half of them correct, or roughly that, you will have a 50%, which is 100% of the possible points. Yes, sir? This is due at 6 instead of 8 because it is something that I decided 6 o'clock was better for me. Yep. Oh, maybe even less than that. All right, someone's asking, what's the minimum I have to do to get 100%? If you get 40% on the showtime, okay, 40% on the showtime, you will get a 40% of the points. You will get 50 points in your grade, which is going to be 50 out of 50. If you do more than the 40%, obviously, it will just help you practice for the test. Yes?
When's the showtime one due?
8 p.m. on Thursday. Yes. 20 questions. They're good practice for the test on Friday. Now, what we've seen today is we're going to be learning about equilibrium. Equilibrium is a dynamic process involving continuous change. So there's a constant change happening. In the block case, you have blocks moving back and forth, back and forth. In this model, you may have used the same blocks and moved them back and forth. Some of you may have even stopped and said, oh, it's the same. Why am I even doing anything? But in a chemical system, the molecules are going one way and the other way. And then different molecules are going back and forth, back and forth, back and forth. The forward rate is equal to the reverse rate in these reactions. When the temperature at which a reaction in the simulation occurs is changed, the particles will change speed. So what is meant by this? Here is a computer simulation. Computer simulation of a reaction that will reach equilibrium. You have A plus BC makes AB plus C. So in this reaction, let's say we start with 50 of these and 50 of these. You'll notice here that they start out with certain amounts. You'll notice in the current amounts, the reactants are both the same amount. The products are both the what? Same amount. Now, they're not staying the same. The reactants are going down a little bit, and the products are going what? Up. So you can see these graphs going down, and this is going up. Eventually, it will reach a state where it's at dynamic equilibrium. At dynamic equilibrium, the concentration of each of the reactants will stay the same. The concentration of each of the products will stay the same. So if you look at the numbers here, it's about 38 and 12, 38 and 12, 38 and 12, 39 and 11. Now, if we pause it and we look at the number in here, the next question is, are all of these products staying together? Or are they breaking up into reactants? Okay. Are all of the reactants staying together? Or are some of them breaking apart into products? Okay. These numbers are constant, but they are changing because If you follow just one of these, and you follow it around, oh, it broke apart. It's hard to follow just one, but if you follow one with your eyes, oh, now it's together. You can see it breaking apart. Oh, now it's to that one. That one, that one. Whoa, where'd you go? It's really hard to follow them, but if you keep track of it, you'll see that the molecule is not staying the same. It's breaking apart sometimes and recombining with other things. If you follow just one of the atoms, you'll see that it is not staying in the same compound, or it's not staying by itself the whole entire time. But the ratio is staying constant, 42 to 8, 41 to 10. Now, if we raise the temperature, what do you think is going to happen when we raise the temperature? Oh, we'll raise the temperature. Let's see what happens. Okay. So we raised the temperature. What happened? What did you see change? Yep. Which numbers? These numbers here? These numbers moved a lot. Very good. Okay, so they're not the same amount as they used to be. Well, are they? No, it looks like it's lower than they used to be. The reactance is lower. But they're still fluctuating quite a bit. They're constant, but they're going up and down, up and down, up and down, up and down a little bit. Okay? The molecules are moving what in this case? Okay, the molecules are moving faster. Now, if we clear this container, and we start again with 10 of these and 10 of these, and we heat it up a little bit, just so it doesn't move too slow. You can see that the equilibrium has been established because the amounts are relatively constant. Again, they don't stay constant the whole time because we have fluctuations. What would happen if I added a ton of A to this? All right. So we're going to add 10 more A's to it. So when we added more A's to it, of course, the first thing we can expect is when we added more A's, the A amount went up, obviously. But what else went up when we added more A's? So let's see if we can zoom in on here. This colored one here is BC. The BC amount was the same as the A. When we added more A, what happened to the BC amount? Went up. Okay? Then it went down. And it went down a lot. What else went up here? Okay, the AB amount. The AB and the C amount, the products went up. So as you can see, when we add more of a particular reactant, it shifts the equilibrium a little bit in this direction. We still have a ton of A floating around, but we got more AB and more C in this reaction. So this computer simulation shows that the temperature at which the reactions in the simulation occurs is changed. The particles change speed, and that could also change the ratio of the reactants to products. Now, much of the world around us depends on equilibrium to maintain balance. The human body maintains balance through a variety of reversible reactions at equilibrium. So if there were not these reversible reactions, our body would not have a balance in many of the functions that it has currently. So reversible reactions and equilibrium are one of the most essential parts of your human body and how it works. The definition of equilibrium, it sounds like Equal-LIV-Bri-Ummm. The definition is the rate of the forward reaction equals the rate of the reverse reaction. So the forward reaction rate and the reverse reaction rate are equal. That's the one thing that's equal at equilibrium. To use it in a sentence, liquid water is at equilibrium with gaseous water in a sealed container. This was the example we showed yesterday. We've got liquid water, we've got gaseous water. They are at equilibrium inside this container. The water is evaporating. The gaseous water is condensing. This is happening constantly, and it is constant motion, but we just can't see it because it's too small. Too small to see the individual molecules moving. But the amount of water in here does not change. We can leave it out for another 2, 3, 4 days, and it will not change. The equilibrium means the forward reaction rate, which is the evaporation, is equal to the reverse reaction rate, which is the condensation. In a chemical equilibrium, you have a chemical like N2O4 being added to another chemical. You have a chemical like N2O4 which breaks apart into NO2. If the reaction starts with a certain amount of this, and you have 0 of this, you'll see that the amounts change over time until they reach dynamic equilibrium. When they're at dynamic equilibrium, the concentration stays the what? Concentration stays the same. Now, is N2O4 and NO2's concentrations the same? No. If you start it the opposite way, you start with lots of NO2 and 0 N2O4. The NO2 combines to form the N2O4, and the concentration goes down. The N2O4 forms, and then the concentration goes up until they reach equilibrium. This dotted line represents equilibrium because the concentrations are staying the what? Same. They're not changing. They're not the same as each other, but they're not changing relative to themselves. The other thing that is constant at equilibrium is the forward and reverse reactions are equal. The forward and reverse rates are equal. So the rate of the forward reaction starts out high and it goes down. The reverse reaction starts out really low. The reverse reaction, there's nothing there to go in reverse. So if there's nothing there, there's going to be no reaction. As you start making some products, those products then react with each other to make reactants. And when it reaches a state of equilibrium, that's the green section, the rates are the same. So the forward reaction rate equals the reverse reaction rate. That is equilibrium. Here's a picture of dynamic equilibrium. If you look at the picture here, you see only reactants, H2 and I2. Here you start to see some HI. Here you see a ratio of the HI and I2. They're all present here. They're all present here as well. In C, if you look up here, it's a little hard to see the white ones, so let me just dim the lights a little bit. In C and D, you'll notice that something is the same in them. What is the same in C and D down here? What's the same in these two? Same amount of purple ones. So plain purple ones. There's a purple. There's a purple. 1, 2, 3, 4 plain purples. 1, 2, 3, 4 plain purples. You have the same number of plain purples. Now, this picture doesn't show them in motion. So these plain purple ones, are they always going to just stay together as plain purple ones? No, they're going to combine and make the HI. They're also going to break apart. The HI is going to break apart into the purple and the white. This is what is called dynamic equilibrium. See if I can highlight that. Dynamic equilibrium. That's when the rate of the forward reaction is equal to the rate of the reverse reaction. And the concentration of the products and the reactants do not change. Okay? They may flip-flop partners, but they do not change in their concentration. The way we can understand this equilibrium process is by using what is called big K. Now, big K may be your favorite store to go to. I heard Walmart is kind of beating it out nowadays. But big K, I know, big K is a ratio. K stands for the equilibrium constant. The equilibrium constant is a ratio that is really easy to calculate. The equilibrium constant is the ratio of the products to the ratio of the reactants. Products over reactants. In our model today, we had a reaction that looked like this. A went to B. Right? What else happened in the reactions we did today? B went to A. So here we use a double arrow. It could look like this. That's a double arrow. The top one's a double arrow. Those are usually the two. Sometimes they even do a double arrow that looks more like this with a center thing in it. That'll work too. When there's a double arrow, that means the system is at equilibrium. Which one is on the product side, B or A, in this equation? B is. It's on the right side, so we're going to say that's products. Reactants are what? A in this case. So now all you have to do is, if you want to find the K for a reaction, the K for part 1. How many B's did you end up with on the end of part 1? 32. How many A's? 16. 32 divided by 16 is 2. So that's your K value for part 1. For part 2, the K is still B over A, but B is what value in part 2? 16, and A was what? 32. That equals 0.5. Now, in part 1 at the end, did you have more products or reactants? You had more products. In part 2 at the end, did you have more products or reactants? Reactants. So, this number here, this K number, if K is greater than 1, it favors the products. If K is less than 1, like this, it favors the reactants. But what if K was equal to 1? What if it was equal to 1? It would favor both or neither, depending on how your perspective is. This is a really, really unique case. It happens like almost never. This actually means you would have the same amount in A as in B. Very rarely happens. Sometimes it does, but very rare. Usually the K value tells you whether the products are favored or the reactants are favored at equilibrium. So this is called big K, or the equilibrium constant. Equilibrium is a dynamic process involving continuous change. Both reactants and products are present in the same mixture, but they're both present at equilibrium. So let's look at this chemical reaction. Okay? After 270 seconds, which statement is true? A, B, or C? Tell the person next to you what you think. Discuss with the people at your table. Ready, set, go. let's raise our hand with a vote. Actually, on the count of three, please say your answer out loud, A, B, or C. 1, 2, 3. B happens to be the answer I got. A is not correct because they will not be equal, even though they're in equilibrium. C, the system is at equilibrium. One reason we know that is because is Z changing? No, after 270 seconds it is not changing. It hasn't changed since 150 seconds. Now, why is it that Z is greater than X and Y? Here's our equation. X plus Y gives us Z at equilibrium. Okay? Now, initially, how many X's do we have? 30. Initially, how many Y's do we have? Initially, how many Z's do we have? 0. Now, what happens is these 30 and 30 come together to make something new, which is the Z. So at the end, this is called equilibrium. Initially, we have 30 and 30. At equilibrium, we have 20 Z's. So how much does 0 have to go up to give you 20? Plus 20. Now, in order to get 20 Z's, how many X's or Y's do you need? How many Y's do you need to make a Z? Huh? Yeah, what's going on with this? How do you make a Z here? You have one X and one Y, and that makes one Z. If I had one Y, I could make how many Z's? If I had one Y, I could make how many Z's? If I had one X and one Y, that would equal how many Z's? One Z. I've got 20 Z's. So how many Y's do I need to use to get 20? 20, thank you. How many X's do we need to use? 20. So we lose, or it changes, 20 X's and 20 Y's go to Z. Not all of them do, right? So that leaves us with 10 X's left over, 10 Y's left over, and 20 Z's left over. And these are all in moles, just to make it easy to keep track of them. What's up? Yeah, 30x plus 30y equals 30z would be great if it was going to completion. But it's at equilibrium, so not all of the 30 are reacting. There's still 10 that are left over. So that's the process. If it was going to completion, yeah, it's just a simple math problem. But this is a way you can keep track of things at equilibrium. You take the initial amount, how much it changes, and then you find the equilibrium amount. So in this particular problem, this is a way of determining why it does the way it does. Okay? Now, if we look here at this picture here, if you look here at this picture, there's 3 different gas mixtures were created and allowed to come to equilibrium. Each symbol represents a different element or compound in the mixture. So, how could you prove that each mixture was prepared with the same number of molecule A? Every single one of these mixtures was prepared with the same number of molecule A. How could you prove that? What is your evidence that they all were prepared with the same number of molecule A, looking at the pictures? What represents A in all these pictures? Circle. So all you have to do is do what to see how many A's are in each of these squares? Okay, count them up. So if we do that here, we got 1, we got 2, we got 3, 4, 5, 6, 7, 8, 9. 10? We got 10 A's. Here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is our evidence that they were prepared with the same amount of A. Now, the A, some of it combined with B or C or D. Have the reactions gone to completion? No. If they went to completion, they would have all what? Okay, all AC or AB or AD, all products. So they have not gone to completion because there's still some reactants and some products. Now, how is the value of K related to the amounts of products and reactants? If we look at the first box, the K value is what? 8.125. Are there more products or reactants here? Reactants. What about the second one? A little bit more products. What about the third one? A lot more products. So what you can see is the value of K determines whether there's more reactants or products at equilibrium. So how can we predict if products are favored in a reversible reaction? To do this, we're going to define the equilibrium constant K and explain the mathematical relationship between the concentrations of reactants and products in an equilibrium mixture, and write equilibrium equations. You're going to work individually. Please recall that brackets denote concentration, which is in moles per liter. That was something from last quarter. That's a way of keeping track of the amounts. So instead of saying I got 8 blocks, it would be I've got 8 moles per liter of this particular chemical. So please turn in your lab manual to the next page over, or next 2 pages over, on lesson number 4. You're going to work individually on lesson number 4 to see. Wait a minute, am I too fast? Lesson 4. Yeah. So in lesson number 4, you're going to look at a particular chemical reaction, and the picture is shown. Okay, we're going to have about 9 minutes to see if we can answer many of these questions, and then we'll go over whenever you can avoid using is, it makes it usually makes a stronger statement. So because if you do like considered or thought to be, you're saying, well, some people think this and then other people think that, instead of saying what you think strongly. So you usually want to make what you don't want to be like, well, there's some people over here that think this is the answer, and then some, instead you'll say film. You would say entertainment is the main use of film. You'd be really strong with your statements. And someone can still disagree with you. No, I disagree with you. I think it's education. That's fine. But you need to be more active in your language to be more confident in what you're saying is based on your ideas and ideas of research or whatever your paper entails. All right, ladies and gentlemen, we're going to look at equilibrium right now. When you have a reversible reaction like you saw in this lesson, both the reactants and the products are present in the mixture. The equilibrium constant K is a numerical value that characterizes the mathematical relationship between the concentrations of the products and the reactants in an equilibrium mixture. In general, the value of K indicates what is present in a chemical system in equilibrium. This is a general way whether products or reactants are favored. In order to get the value of K, we use what's called an equilibrium constant equation. This is an equation that relates the value of the equilibrium constant K and the concentrations of the reactants and products at equilibrium. The concentrations of the products and reactants are raised to their power of the coefficients. So we will take the concentrations and then raise them to the power of their coefficients to get this ratio. This ratio is products over reactants. It's the big K. Products over reactants. But how to write this? To write this expression, this is the most important thing you'll need to know right here. If you write down one thing today and only one thing, this is what I would write down. This is a generic chemical equation for something combining with something else, making something new and something else. A, B, C, and D, just alphabet letters. The little a represents the coefficient, little b the coefficient, little c, and little d. To get the equilibrium constant equation, all you have to do is take the equation, take the first product, put it on the top. The concentration of the first product raised to its coefficient power, which is little c, times the second coefficient, the second product raised to its coefficient power. So those are the products, and then you divide by the reactants. A raised to A and B raised to B. This here is called an equilibrium constant expression. Give you a moment to make sure you have this written down, and then I'll show you how this works in an actual chemical equation. Now, this is a generic equation, so if you only have one reactant, you're going to only have one thing on the bottom. If you have three products, you're going to have three things on the top. But you notice, are there any plus signs in here? No plus signs. So don't just try to take this and put it up here. That doesn't work. It has to be multiplication only for this equilibrium constant expression. So how do we do this? Here's an example. For N2, H2, and NH3, the first product you see is the NH3. What's the coefficient on the NH3? Nope. 2. Coefficient is 2. So NH3's concentration is raised to what power? Second power. Then you do the first reactant, which is N2. Does it have a coefficient? No, its coefficient is 1. So N2 raised to the first power, or just N2 is fine. And then you take the H2, put that down here, and raise it to its what power? Third power. This is called the equilibrium constant expression. That's all you have to do to write an equilibrium constant expression. So we're going to practice writing an equilibrium constant. That's the first step, is being able to write an equilibrium constant expression. So if you look at this equation, here's the equation, here's the products, here's the reactants. Products go on top, reactants go on bottom. Why is this squared? Coefficient is 2. Now this tells you it's a large number, okay? How do you know it's a large number? You have to plug in numbers. But if it's a large number, what's being favored? Reactants or products? Products. So in the picture, you should see more of these. Do you see more of these in the picture? Yep, more of the product. This one here is a small number, so we should see more what? More reactants. Okay? So when K is large, products are favored. When K is small, reactants are favored. What do you mean by large and small? Well, usually here's 1. It's greater than 1 or less than 1. If it gets incredibly small, that means the reaction barely even proceeds. If it's incredibly large, that means the reaction goes towards completion. So very large will not be in equilibrium, so to speak. It's called a completion reaction. So please write the equilibrium constant for this reaction here. The give you 1 minute. Ready, set, go. When you're done, please drop your pencil on your table. Alright, I've heard about 50% of the pencils drop, so let's check our answer here. Which one is going to go on top? Okay, ABA2, which is looks like it's square, but it's on the bottom, so it's not a coefficient, it's a subscript. So AB2 goes on top. A and B squared go on the bottom. Okay, if you got that correct, you can write the equilibrium expression for a chemical reaction. That's all you have to do. All right. Now let's practice writing some K's. Okay, please write the K value for these two reactions. Okay, at this time you may be completed with both or just one. So let's check our answers here. There's the top one and the bottom one, again, for these two equilibrium expressions. All right. Any questions, clarifications? All right, so we've got equilibrium. Now, one thing you'll notice is on this page, all the substances are what phase of matter? They're all gases. Okay, this equilibrium pays attention to gases and aqueous only. The reason why is, let's look at what happens here in this picture. What do you notice is different between the two containers? Okay, the carbon pile. The carbon pile here is bigger than the carbon pile there. The reason the carbon pile is bigger is, who knows? There might have been more carbon in there in the first place. But what is staying constant is the CO2 and the CO and the temperature. So these two systems are at equilibrium. The only thing that matters in equilibrium, though, are the gases and the aqueous. It doesn't matter how much carbon you have here, it will not affect the equilibrium. The carbon can break off and make carbon monoxide or carbon dioxide. The carbon can break off to make carbon monoxide, but then the carbon can form back again. And the amount of carbon doesn't affect this at all. Whether there's a ton of carbon or a little bit of carbon. The way chemists deal with this problem is when you're writing an equilibrium expression, they put in solids and pure liquids, which anything that's not a solution. Solids and liquids, they put their value as 1 in the equilibrium expression. So 1 will, again, not change the value of the equilibrium expression. You can either put a 1 in there or you can omit it completely. But it is the value of 1 for pure solids and liquids. So what would it look like for a heterogeneous equilibria? Please write the K value for this top equation here. What do you think the K value would be for the top equation? Ready, set, go. For the top one, this should be your answer. That's all you need for that answer. Hg2O is solid, so it equals 1. Hg is liquid, so it equals what? 1 as well. So if you really wanted to write those down, you could write them like this. This times 1 divided by 1, but that does not change its mathematical value at all. So you do not include solids and liquids. Please try the PCl5 one. That's phosphorus pentachloride. Please write the heterogeneous equilibrium expression for PCl5 plus water. Okay, which things should not be included? PCl5 and the water. So that is your equilibrium expression for the bottom reaction using heterogeneous equilibria. Now, once you have these equations, if you want to find the value of K, now you just need to plug in some numbers. So this is called an equilibrium calculation. So for an equilibrium calculation, we're first going to look at this experiment. 2 test tubes are added. There's iron chloride and sodium thiocyanate are being added together. Which test tube do you think contains more product? Tell the person next to you. Ready, set, go. Is it test tube 1 or test tube 2? Okay, please raise your hand if you can tell me which test tube you think it is. Which test tube is it that has more product? I hear people saying it out loud, but I can't quite hear them. 2. Yep, 2. That is correct. Why does test tube 2 have more products? What color is test tube 2? It is red, so that means you're going to have more of the products than the reactants. Okay? Now, do you think the 2 solutions are at equilibrium? Tell the person next to you what you think and why. Now, the double arrow represents equilibrium. Is it possible that a solution could be orange and there still could be equilibrium happening? Is it possible that the same amount are going forward and reverse, forward and reverse, forward and reverse? Yeah, absolutely. Okay, just because the ratio of yellow and red is not the same for both test tubes doesn't mean it will not be at equilibrium. The equilibrium process is the fact that it goes forward and reverse. Okay, forward and reverse. So both of these test tubes happen to be at equilibrium. Now, since they happen to be at equilibrium, the question is, will this ratio be the same for the reaction in both test tubes? So to check this out, you're going to turn to lesson number 5 to see if the reaction is the same for both the test tubes. So on lesson number 5, it gives us a visual picture of these reactions. What you're going to want to do is complete at least the table on the bottom of the page, 1 and 2, using the pictures. And then we're going to look at how you got your answers.
students, please go to the outdoor theater for the first ever PTSA Association held at lunch with the possibility of winning an iTunes gift card. Again, outdoor theater for the first ever PTSA Association held at lunch. Thank you.
All right, ladies and gentlemen, we'll talk about our answers. You'll want to try to complete as much of lesson 5 as you can. We'll talk about those results tomorrow.
There's a couple of quests that I did, but on my grade it says 0.
Okay, email me at westview.chemistry,
Alright.
and I will fix that. It's probably because I'm guessing you were at one time in another class and you transferred in. I mean, not transferred in, you switched periods or something like that. That would be why they would be 0, or it could have been a mistake. Your
I have my the lab that
lap.
because I left it at home last night.
Okay.